So today we are going to discuss about the chapter coordination compounds, and in the previous class we already discussed about some of the questions and some of the topics as well. So this is the second part of the last class, that is the coordination compounds 2. Here we will discuss the remaining topics and the remaining past paper questions of the NEET exams from the same chapter coordination compounds. Okay. So first, let me share my screen. I hope this screen is visible. If it is not visible, please let me know. Okay. So in the previous class, we discussed many of the topics from the same chapter. So we have the remaining topics today, and we will discuss the chapters as well. We will discuss the questions as well. Okay. So going to the first remaining topic. So this all we discussed how the compounds are ionizing in water. So now here we have to know how we are giving the IUPAC name for the coordination compounds. So let us take one example here, that is CONH3 5 times ClCl2. How to name this compound? That is the question. Okay. So every time we have to find out the cationic part and anionic part of the compound. So here we have one coordination sphere and one ionization sphere, right? So the coordination, if the ionization sphere here, it is a halogen, that is chlorine. So it will have a charge of negative, that is Cl minus ions will be there in the ionization sphere. So automatically the coordination sphere will be having a positive charge. Now we have to know what is the how many positive charges are there on the coordination sphere. So in the ionization sphere we have two chlorine atoms. So the total charge of the ionization sphere will be each chlorine atoms are having minus. So total 2 Cl minus ions are there. So it is producing total 2 minus charge. So the charge of the coordination sphere will be 2 plus. Okay, so this is the charge of the coordination sphere, and ionization sphere is negatively charged, which has a negative 1 charge. Okay, so here the cationic part will be the coordination sphere, that is the cationic part. The ionization sphere will be the anionic part. Okay, so while naming the coordination compound, the first step is we have to start from the cationic part. So the cationic part here is CONH3 5 times Cl and Cl2 is in the anionic part, right? So if you are starting from the cationic part, here this is the coordination sphere. Now, when we name the coordination sphere, we have to consider the ligands first. So then only we will move to the metal ion. So let us see how many ligands are here. We can see that this is containing 5 ammonia and 1 chlorine. So this is a heteroleptic complex, right? Means the two kinds of ligands are present. Okay. So here while naming the ligands, we have to choose the alphabetical order. So we have two, that is amine and chloro. So we have to name the amine. We have to mention the name of the amine group first, because that is first in the alphabetic order, right? And chloro should be the second one. So we can write it will be pentamine, pentamine. How many chlorine atoms? Only one. So we can write just chloro. So pentamine chloro. Okay. So how this pent came? Pent means we have to mention the number of ligands present. So if it is 2, we will use di. If it is 3, we will use tri. If it is 4, we will use tetra, penta, hexa, like that. So here we have 5 ammonia groups. It means it is a penta. So we can start the name, that is okay, pentamine. Then one more ligand is there, that is chlorine. So pentamine, chloro. Now the ligand parts are over, right? So now we are coming to the metal, that is cobalt here. So the first rule means we have to start from the anionic part. If the anionic part is the coordination sphere, also we have to start from the coordination sphere. Now, while naming the coordination sphere, it is always containing the metal and the ligands. Okay, so we have to start from the ligands first. First name the ligands, then move to the metal. Now here we named the ligand, that is 5 amino group and 1 chlorine. So it is pentamine chloro or chlorido we can use, both are fine. Now the remaining thing inside the coordination sphere is the cobalt metal, right? So now in order to name this cobalt, we have to check the charge of the coordination sphere. If the metal ion present, if the coordination, always the metal will be present in the coordination sphere. So if the coordination sphere is having a positive charge, the name of the metal can be right as itself. Okay. While if the coordination sphere is having a negative charge, the name of the metal should end with ATE. That is the another rule, ATE. So here we know the coordination sphere is a positively charged one. It means the name of the metal can be ended as the name of the metal itself, that is cobalt itself. So this will be pentamine chloro. So we can write pentamine chloro cobalt. So it will be pentamine chloro cobalt. No need to write cobaltate. We will use the name cobaltate when this coordination sphere is having a negative charge. Okay. Now after writing the name of the metal, we have to mention the oxidation state of the metal. So let us find out the oxidation state. So here we can take the oxidation state of metal as X. Okay. Ammonia is a neutral ligand, so it has a zero charge. So 5 into 0 because 5 ammonia. Okay. Then one more thing is there in the coordination sphere, that is chlorine. Only one chlorine. So the charge of the chlorine will be 1 times negative 1. That is equal to, see, according to the rule to find out the oxidation number, the summation of the oxidation state will be equal to the charge of the complex. So here the charge of the complex is 2 plus. So it will be equal to plus 2. If it is not charged, we can write it as 0 here. Okay. So we can write x plus 0 minus 1, that is equal to plus 2. So x will be equal to plus 3. It means the metal cobalt is in plus 3 oxidation state. So here we can write pentaamine cobalt, and the oxidation state should be written in Roman letters. So pentaamine cobalt, pentaamine chloro. Chloro means only one chlorine is there, so don't need to write mono, di or anything. Chloro is fine. So pentaamine chloro cobalt 3. Now we are moving to the anionic part. Anionic part is chlorine. So if it is a halogen, we won't write it as chlorine. We will write it as chloride as usual. So it will be chloride. So the name will be pentamine chloro cobalt 3 chloride. This is how we are naming the coordination compound. Okay. So this is the first thing that we have to remember here. So here we have some examples to find out the oxidation state of the metal. Before that, see this one. Here the potassium is there and this is the coordination sphere. So what is the charge of the coordination sphere here? We have potassium outside the square bracket. Means potassium is a part of the ionization sphere, not the coordination sphere. So two potassium atoms are outside the coordination sphere means there will be total plus 2 charge in the ionization sphere because one potassium is always having plus 1. So due to the presence of two potassium, it will be plus 2. Now for the cobalt, I'm taking the charge X. Before that, what is the charge of this coordination sphere? That will be negative 2, right? Minus 2. Why it is minus 2? Because total plus 2 charge is there in the ionization sphere. So the remaining in the coordination sphere will be minus 2. So it is minus 2 only. Okay, so using the same method, we can find out the oxidation state of the cobalt X. I'm taking it as X. Okay, so because we need the oxidation state for finding out the IUPAC name. So first let us try to name this one. Okay, so using the rule that I explained just now, we can find out the cationic part and anionic part. Here the cationic part is the potassium. Before it was the coordination sphere, but here the ionization sphere is the cationic part and the coordination sphere is the anionic part. Okay, so while naming the compound, we have to start from the cationic part. So here we can start from the potassium. So in case of potassium, the ionic part, if it is positively charged ions such as potassium or sodium, we won't write anything else. We will just write the name of the compound. So we can no need to mention di or di. Dipotassium, tripotassium, because in the previous cases we didn't mention it is dichloride. We just written that is chloride only. So similarly here we can write just potassium. So in the ionization sphere we no need to mention the number of atoms present. In the ionization sphere just we are writing the name, that's it. So here we can write it as potassium only. Okay, so it will be potassium. Now the cationic part is over, right? So now we are coming to the anionic part. Here the anionic part will be the coordination sphere. And so while naming the coordination sphere, as we discussed before, we have to start from the ligands. So here we have 2 ammonia and 4 chlorine atoms. So here also we have to use the alphabetical order. So one is amino, other one is chloro. So we will use amine. So it will be, we have 2 ammonia groups, right? So we will use diamine, potassium diamine. Now, how many chlorine atoms are here? 4. So, tetrachloro. Okay, diamine tetrachloro. Now, that is done. Now, the remaining is only the metal. But here the metal is a part of negatively charged coordination sphere. So, the name of the metal should end with 8. So, we will write it as potassium diamine tetrachloro cobaltate. Okay, now we have to find out the oxidation state. So here we have ammonia, that is 0, chlorine is -1, and the charge of this whole complex will be -2. So we can take the cobalt as 6 and we can write 2x plus 0 into 2 plus -1 into 4, that is equal to the total charge of the ion will be -2. So we will get, so this is not 2x, just x only, because here we have only one cobalt. Okay, so x plus 0 minus 4 is equal to -2. So here x will be -2 plus 4, that is +2. So here we can write it as 2, means the cobalt is in +2 oxidation state. This is how we are finding out the name. So if the coordination sphere is negatively charged, we will write the name of the metal with the suffix at. And if the coordination sphere is having the positive charge, we will mention it first. If it is having negative charge, we will mention the ionization sphere first. So this is the rule. Now we can move to the isomerism in these coordination compounds. We have 4 different kinds of isomerism, structural and stereo. This all we discussed in the previous class. Okay, so we have a linkage isomerism, and that is due to the presence of the kind of ambidendric ligand, means they are having more than one donor atoms, but they will use only one at a time, right? And this is the geometric isomerism. Geometric isomerism means cis and trans isomerism. This also we discussed in the last class. That is, if the same groups are in the same side, that is called cis isomerism. If the same groups are in the opposite side, here that is called trans isomerism. Okay. Now we have the, yeah, so this is the important thing, that is the splitting of d orbital. This can be explained by using crystal field theory. So we have different theories regarding the coordination compounds: Werner's theory, then Valence Bond theory, then crystal field theory, Ligand field theory. Different theories are there. Okay. So another important theory after that VBT, another important theory that we have here is the crystal field theory. So according to the crystal field theory, what is happening, we know that in this coordination compounds, we have the central metal atom, right? So this central metal atom is usually a transition element or d block element. So in the d block element, the valence orbitals are normally 3d orbital and 4s orbital. So during the complex formation, always they are producing the positively charged ions as well. So when they are forming the positively charged ions, the electrons from the 4s orbital will be eliminated and there will be electrons in the 3d orbital, right? So we are considering the 3d orbital for this explanation because for the transition element or their ions, the 3d orbitals are having same energy. Same energy means they all are degenerate orbitals. Degenerate orbitals. So that's why here we can see the 3d orbitals in free iron. Free iron means before the formation of the coordination compound, they are all the 3d d orbitals are having similar energy. So during the approach of the ligands, during the formation of the coordination compound, what will happen? Usually all the 3d orbitals are having same energy, right? That is when the metal ions are free. Suppose if they are forming cobalt, that compound that we discussed before, the compound of the cobalt which is containing ammonia and chlorine ligands, there is a metal that is cobalt. So usually cobalt is in plus 2 oxidation state. So during the formation of that complex, when the ammonia ligands and the Cl minus ions are approaching the cobalt atom, the d orbitals of the cobalt, which are having the equal amount of energy, they will split into two levels. Okay, before that, during the approach, the energies of all the orbital will be increasing. That's why you can see the energy of the orbital means degenerate orbitals are increasing equally. All the orbitals are increasing their energy equally, and now they are having some excited energy level. Still, all the 5 orbitals are having same energy, right? The energies of the 5 orbitals are still same, but they are having more energy than before. That is the difference. Now, when the ligands are approaching, these 5d orbitals will be splitting up into two levels. That is T2g levels and EG levels. So T2g means it will be the combination of dxy, dyz and dxz orbitals. EG orbitals are usually dz square and dx square minus y square orbitals. So these 3 sets and 2 sets will be produced, and in this if the complex is an octahedral complex, the 3 sets, that is the T2g orbitals, will be having lower energy and the EG orbitals will be having higher energy. So this is called splitting of d orbitals in coordination compounds according to crystal field theory. Okay. Now we have to know the electron accommodation in these orbitals in presence of a weak field ligand and a strong field ligand. We have different kinds of ligands. For example, water, then all the halide ions, that is Cl minus, Br minus, all of them are weak field ligands. And the strong field ligands means Cn minus ions, they are also strong field ligands. So when the ligand, then sometimes ammonia is also an intermediate ligand. Sometimes they will act as the weak field. Sometimes they will act as the strong field. Okay. So during the complex formation, the splitting of the d orbital will take place as we discussed before. Then the filling of the electrons in these orbitals will be depending on the strength of the ligand. If the ligands are weak field ligands, means if they are not having enough strength, the electrons of the orbitals will not pair up. At the same time, if the ligands are having high strength, those electrons will undergo pairing and the electrons will pair up. So here we can see the complex CrH2O 6 times. Here water is a weak field ligand, right? So if it is containing 4 electrons, first the T2g orbitals will be singly occupied and the remaining one will move to the higher energy level without pairing with the T2g orbitals. While if you are using this complex, we have Cn minus ligand. Cn minus is a strong field ligand as we discussed now, right? So in presence of this kind of strong field ligand, the electrons will, first the electrons, each orbital will be singly occupied. Then the remaining, we have, suppose we have D4, 4 electrons in the D subshell. as before. So the fourth electron is not going to the Eg level. They will pair up with the first electron of the T2G orbitals. Means due to the presence of strong field ligand, the pairing of electrons will take place instead of making it singly occupied. So this is the role of strong field and weak field ligands. Okay. Now we are discussing about the tetrahedral complexes. We know the shape of the d orbitals because the dxy orbital means it will be between the x and y axis. Dxz orbital will be between the x and z axis. Dyz orbital will be between the y and the z means between y and z axis. The z square will be on the z axis, and the x square minus y square will be on both x and y axis. This is the shape of the d orbitals. Now let us move to the questions from this topic. So we have the first question, that is we have four different compounds. We have to find out the one which is a sigma bonded organometallic compound. So first of all, we have to know what is an organometallic compound, right? So organometallic compounds, from the name itself, it is clear that there will be some organic group and there will be some metal, right? And there will be a metal carbon bond as well. So organic organometallic compounds are containing metal carbon bond. That is the important thing. Okay, so here this will be containing one metal as well. Usually the metal may be lithium, magnesium, aluminium, or some transition metals such as iron, palladium, platinum. Okay, so this organometallic compounds will contain metal carbon bond, and the metal will be lithium, magnesium, aluminium, whatever, any metal may be there. Okay, so a best example for this sigma bonded organo. Then before that, what is sigma bond? Sigma bond means single bond which is produced by the overlapping, the head-on-head overlapping of the atomic orbitals, right? So a best example for the sigma bonded organometallic compound will be always Grignard reagent, because Grignard reagents means they are having the formula RMGX. Suppose R is an alkyl group, suppose R is a CH3 group, okay? So here we can see that if I am writing this in form of the CH3 group, CH3, then this carbon will be bonded to the magnesium, and that magnesium will be connected to the halogen. So here we can see the metal carbon bond. This is the metal, this is the carbon. So there is metal carbon sigma bond, right? So this is an example for a sigma bonded organometallic compound. So the best example is Grignard reagent. Ferrocene, cobaltocene, rutheniocene, they are not, they are actually sandwich complexes. They are they are still organometallic compound, but sigma bonded organometallic compound is sigma bonded organometallic compound is Grignard reagent. So option A will be the correct answer. Now the next question, here we have three different complexes, COCl3 6NH3, COCl3 5NH3, COCl3 4NH3, and we have to find out the correct order of stoichiometries of silver chloride formed when silver nitrate is added in excess amount with these complexes. Okay, so here we have the formula for three complexes, right? So when we are adding silver nitrate solution, that is AgNO3 solution to all these three complexes, what is the number of, anyway they will produce the precipitate. If it is producing the precipitate, what will be the ratio? What is the number of moles of AgCl precipitated in each cases? Let us consider the first one, COCl3 6NH3. Okay, COCl3 6NH3. So this means the compound will be in the form of CONH3 6 times, then the three chlorine atoms will be outside. Okay, So when we are adding AgNO3 solution, silver nitrate solution to this compound, we know that the things inside the coordination sphere will not undergo any ionization, right? The things outside the coordination sphere will only undergo ionization. So here the cobalt and NH3, they won't split or they won't undergo ionization. Only these three chlorine atoms will undergo ionization. So what will be what you will get here? You will get CO NH3 6 times 3 plus complex plus 3Cl minus. These 3Cl minus ions will be precipitated as AgCl. So you will get 3 moles of AgCl. Okay, similarly we can consider the second one as well, that is COCl3 5NH3. It means the compound have the, we can represent the compound that is COCNH3 5 times Cl, because cobalt is an octahedral complex, so always 6 ligands will be there, right? So here one chlorine will be in the ionization, two chlorine atoms will be in the ionization sphere, because inside the coordinate sphere we have only 5 NH3, so it is always a octahedral complex, means one chlorine atom will be should be there to complete the coordination number 6. So two chlorine atoms will be in the coordination sphere. So during the ionization they will produce CONH3 5 times Cl2 plus complex and 2Cl minus. So the 2Cl minus ions will be precipitated as AgCl. So you will get 2 moles of AgCl. Okay. Now let us consider the third one, COCl3 4NH3. Okay. In case of this COCl3 4NH3 as well, we have the same like 4NH3 here. It means 4 ammonia will be in the ionization sphere, right? So around cobalt, the coordination number is 6 always. Means 2 more coordination number to be completed, right? So it will be from 2 chlorine atoms. So inside the coordination sphere, we can see 1 cobalt, then 4 NH3 and 2 chlorine, and 1 chlorine will be in the ionization sphere. So during the ionization this chlorine atom will be precipitated and they will be precipitated as AgCl. So how many AgCl will be here? Only one, because here we have only 1 chlorine in the ionization sphere. So the ratio produced will be 3 to 2 to 1. Means the first one, there's a COCl3 6NH3 will produce 3 moles of AgCl, COCl3 5NH3 will produce 2 moles of AgCl, and COCl3 4NH3 will be producing 1 mole of AgCl. So from this options, the correct answer is option B. The next question, we have to find out the correct statement regarding the MnCN6 3- complex. So we have to choose the correct hybridization and shape of the complex. So here the complex is given as MnCN6 times 3-, right? So here the central atom is manganese, which is surrounded by 6 Cn- ligands. So usually this hybridization and shape can be explained by using Valence Bond Theory. Okay, so in Valence Bond Theory, we have to consider the central atom first, that is manganese. Manganese usually has the atomic number 25 and the electronic configuration will be 3d5 4s2. Now we have to calculate the oxidation state of manganese in this complex. So here manganese is surrounded by 6 Cn- ions, right? So I am taking the oxidation state of manganese as X. Then Cn- is having a charge of -1. So the total charge of the coordination sphere should be, means we have to equate this total charge with the individual charges, summation of the individual charges of the ligand and the metal present in the coordination sphere. So X plus, only we have metal and Cn minus. So metal has an oxidation state of X. Cn minus has a charge of -1. We have 6 Cn minus ions. So I'm taking as X plus 6 into -1, that is equal to the total charge, that is -3. So I can write x minus 6 is equal to -3. So x will be +3. Means the oxidation state of manganese is +3 here. Okay. Now we are going to write the electronic configuration of Mn3 plus ion. We have the electronic configuration of manganese only. We will write it for Mn3 plus as well. So it becomes 3d4 4 is 0. 3d4 4 is 0. So here, in order to explain this valence bond theory, in order to find out the hybridization and shape, we have to write the Parkes notation. So for Mn3 plus 3d4 4 is 0, right? So the 3d orbitals means there will be 5 orbitals in 3d subshell. So I'm writing the 3d subshell. Then we are writing this is the 3D, then this is the 4s orbital, 3D 4s. So we have 4 electrons in the 3D subshell. So I'm writing those 4 and 4s is empty in Mn3 plus ions, right? Now let us consider the ligand. So this is the free Mn3 plus ion. Now, when the Cn minus ions are approaching, we can see that Cn minus, we know that Cn minus is a strong field ligand. This one we discussed just before, right? That is, when a strong field ligand is approaching the central metal atom, the electrons of the metal ion will be undergoing pairing. So here Cn minus ions are having 3d4 4 0 configuration. So when the strong field ligand, when Cn minus ions are approaching this metal, what will happen here? The electrons will pair up. How the electrons are pairing up? See, they will go back and they will pair with the electrons. So in presence of Cn minus ions, the Mn3 plus ions will be as per the given configuration. That is, the 4s orbital is still empty because there is no any electrons. And here we can see, so here we know that Cn minus is a strong field ligand, right? So due to the presence of this strong field ligand, this, as we discussed before, they will pair up. So the electrons will pair up. So we can see after the approach of the ligand, there will be the electrons, that is, one electron will be paired up with the first one and other two orbitals will be having two unpaired electrons. So this is the electronic configuration during the approach of the ligand. That is, three is still, there are four electrons, but from the four electrons, one electron get pair up with the other electron because the Cn minus is a strong field ligand. Now we have to accommodate the electron pairs from Cn minus ions. One Cn minus can donate two electrons, one pair, right? Because it is a monodentate ligand. So during the donation of this electron, we have to make, how many ligands are here? We have 6, right? So 6 orbitals should be free to get the electrons from 6 Cn minus ions. Okay, so we need 6 vacant orbitals to get electrons, 6 electron pairs from 6 Cn minus ions, right? So here we can write the Cn minus during the means in order to accept the electrons we need 6 orbitals, but here we have only two 3d orbitals, one 4s orbital. Total 3 orbitals are free here and we need 3 more orbitals. Right. So in order to get the 3 more orbitals, here it is not available. 3p is filled. So we are not using any inner orbitals. We will use the 4p orbitals in the fourth shell. So we can write the 3d orbitals are having 4 electrons. One is paired, other two orbitals are there. 4s orbital is there and we have to use the 4p as well. So from the 3d we have two orbitals. So from the 3D we have two orbitals, from the 4s we have one orbital and from 4p we have three orbitals. So total orbitals used here will be 1, 2, 3, 4, 5, 6. That is D2 sp3. D2sp3 is the hybridization. So after the hybridization of these orbitals, the electrons will be donated to the vacant orbitals, like one pair will be one here, one here, one here, one here, one here. So now we have total 6 electron pairs from 6 Cn minus ions. So the hybridization will be D2sp3. If the hybridization is D2sp3, the shape of the molecule will be octahedral. Means if the coordination number is 6, the geometry will be octahedral. So the hybridization is D2sp3. So we can omit first one and the third one and the last one. So the second one is the correct answer. It is also given, it is octahedral. So option B is the correct answer. Now let us see the next question. Which of the following has the longest carbon-oxygen bond length? Okay. So here we have four different metal carbonyls. Okay. That is nickel tetracarbonyl, then tetracarbonyl of cobalt ion and hexacarbonyl of manganese. So the bond length between carbon and oxygen, we have to, in order to explain that, we have to see which metal is having the maximum charge. So here in case of FeCO4 times 2 minus, here we can see the metal atom will be having maximum negative charge. If I take it as X, the carbonyl group is a neutral ligand. So X plus 4 into 0 is equal to negative 2. So X will be negative 2. Similarly, if you find out the charge of NiCO4, that will be in 0. Here nickel is in 0 oxidation state. And in the second one, it will be in minus 1. In MnCO 6 times, the manganese will be in plus 1 oxidation state. But in the third one, FeCO4 times 2 minus, the ion is in minus 2 oxidation state. It means the electron density is more on iron. So when the electron density on the metal is increasing, electron density on the metal is increasing, there is a possibility for pi back bonding. Pi back bonding. It means usually the metal ligand bond is produced when the ligand is donating the electrons to the vacant orbital of the metal. This is how the bonds in the coordination compounds are producing. Similarly, when the electron density on the metal is increasing, there is a possibility in which the metal can give the electrons back to the ligand, and that donation will be to the anti-bonding orbital of the ligand. So this is creating a double bond effect. Usually the metal ligand bond will be a single bond because metal is giving electron to the ligand. But when the ligand is giving electron to the metal, when if there is if there is any chances of high electron density on the metal, there is a possibility in which the metal can donate the electrons back to the antibonding orbital of the ligand. That is called back bonding, and this is producing some double bond character between the metal and the ligand. So here the ligand is carbonyl group. Okay, so here due to the back bonding, this back bonding is happening when the metal is having more electron density. So here more negative charge is present on the metal in case of the third one. So more negative charge means more electrons will be concentrated on the ion in the third one, right? So when the electron density on the ion is increasing, ion will give electrons to the antibonding orbital of the carbon. So here there is a possibility in which the metal carbon bond, that is ion carbon bond, become more strong. Okay, when it is more strong, it will produce the back bonding. That is, here the bond length will be less. So the correct answer will be option C. Because here the metal carbon bond strength is increasing. So when the metal carbon bond strength is increasing, this bond length will decreases. Means the metal carbon bond length will decreases. When the metal carbon bond length is decreasing, the carbon oxygen bond length in the ligand will increases. So here they are asking about the carbon oxygen bond length. So if they are asking about the metal carbon bond length, it will decreases. But when the bond between the metal and the carbon becomes strong, the bond between the carbon and oxygen present in this ligand become weak. So this is strong, but this become weak. So here the weak bond will be having higher bond length, right? So FeCO4 2 minus will be having longest carbon oxygen bond length. They are not asking the metal carbon bond length, carbon oxygen bond length. So that will be higher in third one. So option C is the correct answer. Now the next question, the ionic radii of A plus and B minus ions are given here. They are 0.98 times 10 to the power minus 10 meter and 1.81 times 10 to the power minus 10 meter. We have to find out the coordination number of each ion in AB. Okay, so first we have to take the ratio between the radius. Okay, radius ratio will be, that is the radius of the positively charged species divided by the radius of the negatively charged species. So here the positively charged one is A plus, which has the radius 0.98 times 10 to the power minus 10, and the negatively charged one is having a charge radius 1.81 10 to the power minus 10, and here the ratio will be 0.541. So from this range we can find out the coordination number, because if the radius ratio range is between 0.414 to 0.732, the coordination number will be 6. This thing we have to memorize, then only we can predict the answer. So here the 0.541 is between 0.414 and 0.732, right? So when this ratio is between this range, the coordination number of the complex will be 6. So here the correct answer is option A, that is the coordination number is 6, and here it will be in octahedral arrangement. Coming to the next question, here we have different ions or ligands. We have to arrange them in increasing order of their trans effect. So first we have to know what is trans effect. The trans effect is an important concept in coordination chemistry, okay? And this is particularly observed in square planar complexes. Square planar complexes of the transition metals such as platinum. Okay, now this is referring to the ability of a ligand to influence the substitution rate of another ligand which is positioned at the trans position. That is important. So the trans effect can be defined as, it refers to the ability of a ligand to influence the substitution rate of another ligand positioned trans to it. Trans to it means opposite to it. So this is called trans effect. Okay, so here we have four kind of ligands. So we have to arrange them in increasing order of their trans effect. So all the ligands can be arranged in the order of their increasing trans effect. Usually it will be, means more trans effect will be for always Cn minus ions, then carbonyl group, then Br3, then H minus, CH3 minus, I minus, then Br minus, then Cl minus. Then least is ammonia, then more least will be water. So based on this order, we can write Cn minus will be the highest trans effect one. The next one will be C6H5 minus, the next is Br, next is NH3. So here we have the correct answer, that is D. Next is, we have different d electronic configuration here. We have to find out the one which cannot show the Jahn-Teller effect. Okay, so we have to know what is Jahn-Teller effect. Usually the Jahn-Teller effect is occurs. So the Jahn-Teller effect is usually occurring in the coordination complexes when the electronic degeneracy leads to the geometric distortion. Means it will lowers the energy of the system, and it is most commonly observed in octahedral complexes and sometimes in tetrahedral complexes as well. Octahedral and tetrahedral complexes. Okay, so this effect is occurring in the coordination complexes when the electronic degeneracy is leading to the geometric distortion, and it is lowering the energy of the system, and it is most commonly observed in octahedral complexes, sometimes in tetrahedral complexes as well. Okay, so this is the thing. Now we have to see the correct answer here. That is, the John Teller effect is not observed in which of the complex. So here we have in unsymmetrical octahedral geometry, the John Teller effect explains the it will affect the distortion, right? So it will be in D8 complex. So in D8 complex, the John Teller effect will be absent. Especially this is here it is given that for high spin complexes they are asking. So if the D8 complex is a high spin complex, it will be having it will not be having the John Teller. It cannot show the John Teller effect. So the correct answer is option. So the correct answer is option D. That is the D8 configuration. Now the next question. In calcium fluoride having the fluoride structure, the coordination number for calcium ion, that is CO2 plus ion, and fluoride ions will be which one? Okay. So here we have to name the given coordination complex. The complex is given as FeCN6 times 3 minus. So we already discussed how to name the coordination complex at the beginning of this class, right? So as we discussed before, we have to start from the cationic part, then the anionic part. But this complex is only having the anionic part. So we are not thinking about the cationic part because this is only one species with a negative charge. So this is the coordination sphere as well. So in the coordination sphere, while naming, we have to start from the ligands. So here the ligands are Cn minus ions. We have 6 ligands as well. So in the coordination sphere, we will name the ligands first, then only we will move to the metal ion, right? So it will be 6 means we have to use the prefix hex. So it is hexa, then Cn minus will be cyano. So it is hexacyano. Then the central metal atom is iron. So here the metal ion is a part of negatively charged complex ion. So the name of the metal will end with the suffix ate, right? So it will be hexacyano ferrate. Now we have to find out the oxidation number. So the oxidation number of iron can be taken as X, and Cn minus is having a minus 1 charge. So it will be X plus 6 into minus 1 is equal to the charge of the complex, that is minus 3. Then X minus 6 is equal to minus 3. X is equal to plus 3. So the oxidation number we have to provide in Roman letter. So the name of the complex is hexacyanoferrate, and this is not a neutral species, and the cationic part is not given. So this is a negatively charged ion, right? Means this complex itself is a negatively charged ion. So we can write it as, this is an ion. So we can write hexacyanoferrate 3 ion. This is the name of the complex. So the first one is incorrect because it says the tricyano. No, wrong. Now coming to the other options, all of them are hexacyano. So coming to the second one, cyanidoferrate 3 ion, that will be the correct answer. Because ferrate and cyano or cyanido both are fine. So correct answer is B. And the last one, hexacyano iron. We cannot use iron. That is a wrong abbreviation. So this is also wrong. And coming to the last one, hexacyanidoferrate 3 iron. Cyanido we cannot use. We can use either cyano or cyanido. So option D is also wrong. So the correct answer is option B. Next question. We have to find out the hybridization involved in the given complex. So the complex given is NiCN4 2 minus. So we can start from the complex NiCN4 2 minus. So here we have to explain this by using valence bond theory as we did before. So nickel is the central atom. Nickel has an atomic number of 28. So we can write the electronic configuration 3d8 4s2, right? Now what is the oxidation state of nickel in this complex? We have to calculate it. I'm taking the oxidation state of nickel as X. So X plus 4 times negative 1, because 1 Cn is having a negative 1 charge, that is equal to minus 2. So X minus 4 will be equal to minus 2 and X will be plus 2. Means nickel is in plus 2 oxidation state. So I'm considering Ni2 plus ion, that is 3D8 4s0. In order to find out the hybridization, I have to write the box notation. That is 3D8 configuration. The 3D orbitals are having 8 electrons. So first I'll fill all the orbitals singly occupied. Then I'll do the pairing. That is the rule, right? Now 4s orbitals are empty. 3D orbitals are having these many electrons. Now I need to check whether the Cn minus is a strong field ligand or weak field ligand. Cn minus is a strong field ligand. So when the Cn minus is approaching the metal, there will be a pairing of electrons, because here during presence of a strong field ligand, the electrons of the metal ion will pair up, right? So when the Cn minus is approaching, the electrons will go to back and they will pair up. So here we can see that there is no any electrons in the 3D orbitals, right? So the electrons in the there is no electrons in the 4s orbital. We have electrons only in the 3D orbital. So here we have one d orbital vacant now, and one 4s orbital is also vacant. Now we have to check how many Cn minus ligands are coming. Here we have 4 Cn minus ligands. So the in coordination ligands are giving their pair, means lone pair of electron to the vacant orbital of the metal. So here we have 4 Cn minus ions, right? So we need 4 vacant orbitals. Okay, 4 vacant orbitals we need. But here we have only 2, one 3D, one 4s. So in order to get 4 vacant orbitals, we have to use 2 more orbitals from the 4th shell. So 4 is already there and we have to use the 4p subshell as well. But in 4p we have 3 orbitals, but we need only 2. So here one 3D, one 4s and two 4p orbitals will hybridize together. So after the hybridization, the electronic configuration will be like this. These orbitals will be 3D and these are the hybridized orbitals. That is 1D, 1s and 2p. So the hybridization is DsP2 hybridization, and one 4p orbital will be unhybridized. We are not taking care of it. So here we have 4 hybrid orbitals. So to each hybrid orbitals, each Cn minus will be donating the electron. So we have total 4. So the hybridization is DsP2 here. So from these options, we can see that the correct option is DsP2, option C. Now the next question, here one complex is given. Here the question is the sum of coordination number and oxidation number of the metal in the complex Men twice C2O4Cl. So oxidation number and coordination number. So coordination number is the number of ligands surrounding the metal, right? So here M is the metal, it is a random metal which is surrounded by 2 ethylene diamine and oxalate ions. Okay, so 2 ethylene diamine and oxalate ion means the total coordination number will be 6 here. Now we have to find out the oxidation state. So in order to find out the oxidation state, I am taking the oxidation state of the metal as X. So X plus ethylene diamine is 0, 2 into 0 plus oxalate ions are having a charge of minus 2. The complex is having a charge of plus 1 because ionization sphere is having only one chlorine. So we can write X minus 2 will be equal to plus 1. So X is equal to plus 3. So coordination number is 6, oxidation number is plus 3. So the summation of coordination number and oxidation number will be 6 plus 3, that is 9. So correct answer is C.